Good morning. Today we're going to talk about Math 101, and we're going to start talking about Chapter 7, entitled Factoring. All right, in particular, we're going to start with Section 7.1, Chapter 7, Section 1, which talks about factoring monomials from polynomials. All right, a topic I'm sure we've seen before. Let's start out with a working definition of what it is to factor. Let's see, to factor, the verb version, to factor means to equivalently rewrite a sum of terms as a product of factors. All right, notice a term is a piece or an element of a sum, and a factor is a piece or element of a product. Okay? So we start out with sums and typically end up with factors when we factor an expression. Let me give you an example here. If we ask us to factor, let's just start something simple, 6x plus 18. Well, your first task should be to spot the GCF, greatest common factor, and C is the major word here. C for common. It's got to be common to both terms of the sum. All right, clearly the GCF here is going to be 6. If I look at these two terms, all right, 6 is the greatest quantity that's a factor of both terms. All right, so I can factor it out according to my distributive law. I could call this equivalently 6 times x plus 3. Notice, if I'm working in this direction, I'm factoring the expression on the left and taking a sum and rewriting it equivalently as a product, right? We could check it. 6 times x is 6x, and 6 times 3 plus 6 times 3 is 18. So working right to left, we can factor. Notice, if we go right to left here, we're multiplying. Again, 6 times x is 6x plus 6 times 3 is 18. So in some ways, factoring can be referred to as the reverse, or some say the inverse, of multiplication. All right, let's dive in and do some examples now. Let's see, example 12 in our text. This is on page 406. Asks us to factor the simple expression 15x minus 20. All right, what's the GCF? What's the greatest quantity that's a factor of both terms of this sum or difference? Well, I think we'll agree it's 5. 5 is the greatest quantity that's common to both terms. So I can factor out a 5 in common language from that binomial difference. All right? If I take out a 5 from 15x, I'm left with a 3x in the first slot, minus, factoring out a 5 from the second slot gives me a 4. So final answer, 5 times 3x minus 4. Notice we started with a sum or difference of terms, and we were left with a product of factors, hence the title factoring. Okay? All right. Let's go on to example 13. Example 13 in our text on page 407. asks us to factor the expression 3y squared, 6y squared, 6y squared plus 9y to the fifth. Now, of course, not all greatest common factors are just numbers. Here we've got some powers of y that are common to both terms. What I do is I look at the coefficients first. I'll spot the GCF of the numbers or coefficients first. It looks like 6 and 9. The greatest common factor of 6 and 9 is 3. And I've got 2 factors of y in this term. I've got 5 factors of y in this term, so I can factor out the common powers of y. So my GCF is 3y squared. So I want to now rewrite this equivalently as a product of factors. I'll get 3y squared. What's left in the first slot? Well, if I factor out a 3y squared from 6y squared, I'm left with a 2 in the first slot. And if I factor out a 3y squared from 9y to the fifth, I'm left with 3y cubed. Again, you can check your answer by multiplying. I won't take the time here. I'll just say this is my final answer, 3y squared times 2 plus 3y cubed. Let's look at example 14 on page 407 again. And this one's a trinomial. Factor 8q cubed minus 20q squared minus 12q. All right, what's the GCF? Well, if I look at the coefficients 8 and 20 and 12, looks like the GCF of the coefficients is going to be 4. 4 is the greatest quantity. That's a factor of 8 and 20 and 12. Now look for common powers of variables. I've got 1q here, and I've got only 1q common to all 3. You have to be common to all terms, right? That's what the C stands for in GCF. So I can factor out a 1q, so my GCF is going to be 4 times q. So rewriting this as a product, I'll factor out the 4q. All right, from the first slot here, the first monomial, if I factor out a 4q, I'm left with 2q squared minus factoring out a 4q from 20q squared, I'll get 5q minus factoring out a 4q from 12q, I'll get a 3, just a simple 3. Final answer, 4q times 2q squared minus 5q minus 3. Example 15. Also on page 407. Factor the following expression. And I believe there's a common mistake that happens in a problem like this, so listen up out there. 35x squared minus 25x plus 5. All right, what's the GCF? Well, again, the GCF has to be common to all terms, and I've only got a number here, so it looks like 5. That's the only thing that would qualify as a common factor to all 3 terms. All right, so I believe I can factor out a 5 here. I'll get 5 times what? Well, if I factor out a 5 from the first slot, I'll be left with 7x squared minus factoring out a 5 from the second slot, I'll get 5x plus, well, if I factor out a 5 from this third slot, well, I'll have to leave an invisible 1. Notice 5 is 5 times 1. If you factor out the 5, you're left with 1. And multiplying it out will again confirm this. Final answer, 5 times 7x squared minus 5x plus 1. Example 16. A little nastier still. Climbing up the ladder here, page 407 again. All right. Factor. Four x cubed plus x squared plus 8x squared y. All right. Looking at this one term at a time, I've got a series of 3 terms here being added, so it's a trinomial. What's the GCF? Well, let's see. Looking at the coefficients, x squared is really 1 times x squared. All right, so I can't really factor out from the coefficients anything meaningful unless you want to factor out a redundant 1. All right. So I'm left with the powers of x to deal with. Let me rewrite that second term, x squared, in the second slot. All right. Anything common from the variables? Well, I've got x cubed, x squared, and x squared y. I cannot factor out a y, right? There are no y's in any of the other terms, so it's not common. But of course, 2 factors of x are common to all 3 terms. So I'll factor out an x squared, and that's all I can factor out. X squared then times 4x plus, well, again, if I look at the second slot and I factor out x squared, I'll have to leave the invisible 1 in its wake, plus 8y in the third slot. Final answer, x squared times 4x plus 1 plus 8y. All right, example 17. On page 407, asks us to factor the following expression. X times 5x minus 2 plus 7 times 5x minus 2. All right, now do not multiply. We are asked to factor, and remember, factor is the reverse or inverse of multiplication. All right, I'm hoping that we'll notice something. 5x minus 2 seems to be repeated here. That suggests something. Let me highlight that. All right, 5x minus 2 here, and 5x minus 2 here is indeed a common factor to this indicated sum here, is it not? So I should be able to work my distributive law in reverse and factor out the common factor of 5x minus 2. All right, so that's what I'm going to attempt to do here. All right, 5x minus 2, again, I've got 2 factors of 5x minus 2. So I can factor out the common 5x minus 2. Don't forget to wrap it in parentheses. Times, well, what's left? In the first slot here, I'll have an x that's left. And in the second slot here, I'll have a 7 that's left. So final answer, 5x minus 2 times x plus 7. So indeed, we can see here that GCFs don't have to be just numbers, don't have to be just numbers and variables. They can also be more complicated expressions as seen as common factors. Example 18 in our text is similar. This is on page 407, right at the bottom. We are asked to factor 4x times 3x minus 5 minus 7 times 3x minus 5. Very similar to the last problem, again, I'll notice 3x minus 5 is a common factor to both terms of this difference. All right, so I'll take out the common 3x minus 5. What's left? Well, in the first slot, there's 4x. And in the last slot, minus, I'll have minus 7. Final answer, 3x minus 5 times 4x minus 7. All right, we'll call it a day here with example 18. This concludes section 7.1, factoring monomials from polynomials.